Assalamualaikum warahmatullahi wabarakatuh. So welcome back to my video. So let us continue with still chapter number 3 on the example number 6. So 460 volt. So this is the terminal voltage of the motor, right? So again, so this is the P in horsepower. So we have the FE, so number of pole, and then the Y connected one rotor induction motor. So this is the type of rotor. So if you still remember last time, basically we have two type of rotor of the induction motor, namely the squirrel cage as well as the one rotor. So has the following impedance in ohms per phase referred to the stator circuit. So we have R1, X1, R2, X2 plus XM. So now the question, what is the maximum torque of this motor? So something like your T max, okay, or the pull out torque, and what speed and slip does it occur? So you need to find the value of an M and also the slip S. B, what is the starting torque of this motor? So the T start, right? The T start, and then when the rotor resistance is double, again, if the rotor resistance is double, so we have R1 is, for example, double. So, oh, not R1, but this is R2, for example. So what is the speed at which the maximum torque now occurs? So what is the new starting torque of the motor? Okay. Now solution number 6, the terminal voltage again. So you just take your equation of terminal voltage and immediately substitute the value of SM, R1, X1, and XM. Okay, just complete the calculation to get the value of terminal voltage is approximately 255.2 volt. And then same goes to terminal resistance. We have approximately R1 in bracket SM over X1 plus SM squared, and solving the calculation of the steps may giving us the value of terminal resistance approximately 0.590 ohms. And then what about the terminal reactance? So this is what we have seen earlier. So it is somehow approximately equal to X1, and we can actually directly obtain from the provided value. And then what's next? So the slip, so at which the maximum torque occurs is given by equation below. So we have seen this quite sometimes. So the equation or the formula of pull out S or maximum S. So we have R2 over blah blah blah, and then again, so since we have done with RTH, XTH, and so on, so forth, so replace or substitute the value giving us the maximum pull out torque, or sorry, the maximum slip that the pull out torque occurs is about 0.198 or 19.8%. And this corresponds to a mechanical speed of an m equal to 1 minus s and sin, so minus 1 minus 0.198, so 1800 revolution per minute. So giving the corresponding speed of the mechanical or the mechanical speed of the motor is approximately 1444 revolution per minute. And then what about the torque, the pull out torque? So again, so just use the equation we obtained earlier. So VTH, RTH, blah blah blah. And then from here we may get that the pull out torque or the maximum torque, okay, is around 229 Newton meter. B, the starting torque of this motor is found by setting is equal to 1, because at starting torque normally, so we know that the N and the mechanical speed or the motor speed is equal to 0. So whenever speed is 0, we know that the slip is actually maximum 1, because again S is fall in between 0 and 1. So this is at still or rotor stop, right? Where Nm equal to 0, and here happen at n m, the mechanical speed equal to the n sin. Okay, the maximum synchronous or rotating magnetic field. Okay, and then T start equal to VTH blah 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 blah. Again, substitute all the value, giving us the starting torque of this motor is equal to 104 Newton centimeter. So if the rotor resistance is double, so then the slip at maximum torque doubles too. Therefore, now instead of 0.198, we multiply by 2, so to get S pull out equal to 0.396. Okay, and then the speed at maximum torque is again, so Nm equal to 1 minus S and sin. So substitute the new value of S to give a new speed, okay, of motor at this maximum torque. And then the maximum, besides this maximum torque is still to T pull out equal to 229 Newton meter. So this is from the previous calculations. Okay, the starting torque is now again substitute the value of VTH R2 blah blah blah. So again this is from here, sorry, the omega sin over here is actually from the equation of Nm, okay, or N sin equal to 120 FE over P, which I believe from the question earlier, the value is 60 Hz over 4, and giving the N sin equal to 108,000 RPM. And once you convert to omega sin, so just divide by 9.55. Right? And thus you may get the value of omega sin in radian per seconds. And therefore, T start equal to 170 Newton meter. Okay. So we have done with example number 6. So let's continue with subtopic of how to start the induction motor, or starting the induction motor. So simply start the induction motor by connecting them to the power line. Of course, you need the supply. So may cause voltage dip in the power system. So the voltage dip over here caused by the inrush current, the high inrush current going into the system whenever you switch on the machine. Okay, then what happens if we have the one rotor induction motor, the one rotor type of induction motor, so the insertion of extra resistance. So you insert the extra resistance may increase the starting torque and reduce the starting current. So this is one advantage, or this is actually one of the very effective and significant method in order to reduce the starting current here. The high starting current, the inrush current may go up to 6 times of the rated current, for example. And by inserting the extra resistance, so it may reduce the current and also increase the starting torque. So having a high starting torque giving an advantage to motor to be easily spin or to be easily rotated. So what about the squirrel cage induction motor? The starting current depends on the rated power S start in kVA. Okay, this is actually the apparent power, and the rated voltage VT, terminal voltage in volt. Okay, so the rated power, S start, the rated power, the apparent power start equal to rated horsepower. Okay, I think this is a wrong spelling. Horsepower multiply times code letter factor. So the code letter factor is decided by the factory itself, or the NEMA, the National Electrical Manufacturer Association, that produce that actually standardize the manufacturing of the machine, and each machine has been categorized into several code letter or code, namely A, B, C up to V, and we will see this in more details in the following slides. However, this is the equation or the formula of IL. Okay, so we want to know what is the value of IL if we have the rated power as start and also the terminal voltage B, Vt multiplied by 3. Okay, so the S start is from the rated power, and then remember to multiply with the chord letter of the chord letter factor of the motor. So this is the table of the chord letter in kVA over HP horsepower is given on the nameplate of the motor, the birth certificate, if I would say. Okay, and then the example of chord letters, so nominal chord letter, so type of machine, for example. So it also reflects or represent the type of machine, so from A up to Z. So it depends on the log rotor and the result. So this is the range of the kVA over HP. Okay, so 4 to 5, 4.5, for example, for D. Okay, for K we have 9 up to 9.0. Now, to have a better understanding on how to use start codes or the start letter codes, consider the example below. So we have 440 volt Vt. Okay, so we have the P, the horsepower HP. So induction motor has start code H. Okay, the H table is fall in between 6.3 up to 7.1. Okay, so we have the kVA over HP range from 6.3 up to 7.1. So find the maximum current that may be expected at starting. So we want to predict what is the maximum current may occur at the starting of the induction motor. So from the start code class, H has a maximum kVA of 3.1 multiplied by the rated horsepower. So here we take the maximum one since we want to obtain the maximum current. So take the value, the maximum limit over here, 7.0, so multiply by the HP, okay, the horsepower. So this is what we have seen in the previous equation. So S start 7.1, so here 7.1, the chord letter, so multiply by 50, giving us the value of parent power or the rated power equal to 355 kVA. So therefore, the start current is, so this is, you may actually get from, again, equation in previous slide where we have S IL equal to S start, S start, so over 3 square root 3B Vt. So S start, the one we calculate here, okay, taking consideration the value of 7.1, okay, the code letter, the code letter, and then we have this IL equal to 355 times 10 to the power of 3, okay, kilo, and then divide by square root 3 multiplied by Vt, which is 480. So thus, the value of starting current is 427 ampere. So starting induction motor again, so this is actually another method of how we can reduce the high inrush current or the high starting current. So starting circuit is used to reduce starting current, but it also reduces the starting torque. This is the main problem. Once you reduce the currents, so the starting torque may also reduce. So common approach is to reduce the motor's terminal voltage during starting by using auto transformer. So this is quite common. Instead of the variable control of the frequency, for example, now we have the auto transformer in order to control the inrush or the starting current. So how it works? So look at this diagram. So we have our transformer over here, the one I write in the yellow box. So this is the transformer. So we have the middle tab over here, and then we have the contact over there, contact number 1, contact number 2. So contact number 1, so they are in 3-phase. Okay, so we have 3-phase. Okay, we have line number 1, so we have line number 2, the line terminal, as well as the line number 3 that connected to the motor terminals. Okay. So we have motor terminal number 1, for example, terminal motor number 2, and number 3. So what happened? So first contact 1, if you give a supply, so through L1, L2, and 3. So contact 1 and contact 3 here. Alright, so let me circle contact 1 and contact 3. So simultaneously, the rest will follow. Okay. So contact 3 are shut or we close. Okay, getting here, so it is getting here to close the circuit. Okay, so the current will flow. So from terminal L1, for example, down to 1, so to the transformer, may detect over here and go to the terminal 1 of the motor terminal. Supplying lower voltage, of course, because we tap out in somewhere in the middle over here. That means we start with the lower voltage rating in the beginning to the motor. All right, and then step number 2. So when motor is nearly up to the speed, so it's trying to run up. Okay, and then number terminal or contact 1 and 3 are now open. 1 and 3 are now open, and then contact 2 shut. So we close contact 2. Okay, close contact 2. So that means circuit over here is now being connected. Okay, number 2. And give full line. Okay, here give full line to the line voltage across the motor. Okay. Yeah, this is how the current flow. Right? Similar thing, similar direction to what I have shown you earlier. Okay. All right, the animation here and here and here. Okay, 2 techniques to control the speed of induction motor. So we have first vary the NSync. So to change the value of FE and also the pole, because we already know and we frequently write that NSync equal to 120, oops, not E, but 120 FE over P. That's mean by changing P and FE may vary the synchronous speed, and then we are able to control the speed. And then the second step is to vary the slips by changing VT and also the rotor resistance. So why slip? Because we know that how to relate between slip and M, because we know that the speed of the motor is rely on the slip of the rotor of the motor. Okay, and sync. Okay. So how to do? By changing or varies the value of terminal voltage and also the rotor resistance. Changing pole is now greatly obsolete nowadays currently. Okay, this is very old technique and is no longer applicable in current days. So changing line frequency. So from the frequency over here, so let's changing line frequency. So from the below equation over here, so we know that the induced flux is equal to minus Vm over omega Np, okay, cos omega t. So what happens if we decrease the value of f? So inside omega we have 2 pi, so we have 2 pi f. So decreasing the value of f may cause the cos is approaching the degree is approaching 0. So approaching 0 means we have almost 1 over here, so we have almost a maximum Vm over omega and p. Okay, and this may cause this flux is increasing. Okay, so and thus excessive magnetization current so may cause the flaw in the motor, okay, because the induced flux may induce the magnetization current. Okay, so excessive magnetization current so may harm your motor, of course. So to decrease the magnetization current, so voltage applied to the stator need to be decreased. So this is another technique. It's order again to decrease the magnetization current. So we decrease or we try to decrease the voltage applied to the stator. And therefore, maximum power rating of the motor must be decreased to avoid motor overheat. So this is the relationship. Okay, the P equal to V square root 3 VL IL cos theta. And then next, determining the circuit model parameters here. So why this is important? Because this is actually to determine or to plot out the torque speed curve, the torque speed characteristic of the real induction motor. Okay. So what are those parameters? So we have seen R1, so we have seen R2, so we have studied S1 and came across X2 as well as SM. Okay. So what tests involved? So we have a DC test. This is to find stator resistance R1. So we have the second test, which is a no load test. In order to find Z no load, consists of X1 and also XSM. Okay. And then last but not least, the lock rotor test. So we block the rotor. That means the rotor doesn't move. We put on hold the rotor while it is running and stop it immediately, or we hold it immediately in order to find the lock rotor R, consists of R1, R2, and the returns XLR, X1, and X2. So first, yes, this is a DC test. We will see in more detail how to perform the DC test. This is another diagram of the equivalent circuit. So current limiting resistor over here. So we have VDC variable. Okay, so we have just directly supplied to your terminal of the motor. Okay, especially at the terminal number 1 or terminal number 2, for example. We pick the first two terminal, consists of R1 and R1. So this is balanced system. So we have our ammeter that connected in series and voltmeter connected in parallel. So what next? So the step is first DC voltage applied to stator winding. Okay, so we have DC voltage over here. This is connected to the stator winding over here. So we have, then since it is DC, does no induced voltage. So no voltage will be induced, and there is no induced I2 at the rotor. And then Jx reactance equal to, of course, equal to 0. So what do we have is actually two elements, which is VDC and also IDC. It's a direct forward element of electric. So I1 is adjusted to L1 rated. Okay, so it depends on the rated current of the motor. And then voltage between terminal is measured over here at these 2 points. So it's being measured. So the total resistance to R1. So we have R1 over here, the first R1. Okay, and then the second R1, for example. So R1 plus R1, we have 2 R1. So this is equal to VDC. So the measured V over here, so VDC, so divided by IDC. So and then from there, you are able to calculate or to obtain the value of R1. So what about the no load test? Okay, the no load test over here is actually to, oops, all right, okay, here. Okay, this is the diagram on how we can experimentally set up our no load test. So we have variable voltage, variable frequency, 3-phase power source. So we have our voltmeter over here in between line 1 and line 2. So we have our power meter P1 and P2. Okay, we have ammeter in series for line 1, line 2, and line 3. So we have the respective current IA, IB, and IC. So the no load over here. So we have IL. So there is no load, the motor is not connected to any load. And then we have IL equal to IB plus IA plus IB plus IC over 3. Okay. And then this is some of the I would say the power of the motor. So we have P in equal to P SEL, so the stator copper loss plus P rotational. So what is P rotational? P rotational is nothing but P core plus P friction and windage plus P stray of this miscellaneous. Meanwhile, P SEL equal to 3I1 square R1, And then the magnitude of ZEQ equal to V phase over I1, no load. So approximately equal to X1 plus XM. Okay, so that's means from here we are able to obtain the value of X1 and XSM by calculating the ZEQ. Okay, how? So we have V phase over I1 during no load. Okay, so we have V phase over here divided by I1, for example. Okay, so the meter of voltmeter ammeter over here may give the result to calculate ZEQ. So what about the equivalent circuit? So here we can understand that since we have, okay, let me write for you, or let me draw for you. Again, the equivalent circuit of the IM induction machine. So we have resistor over here, and then we have coil over here. All right. So what else we have? So we have the JX2 and also the R2 over here, and then we have the R21 of minus S over here. So remember this type of equivalent circuit. We have R1 over here. So what else? JX1. Okay. So we have RC over here. Okay, and then we have JXM. All right. And then over here we have let's say JX2. We put JX2 over here, and then we have R2, and so this is the fundamental equivalent circuit of induction machine. If you can recall, okay, 1 minus S over S. Okay. Now since R2 1 over minus S over S is much greater than R2. Okay. And R2 1 over minus S over S is much greater than grand X2. So what happened next? So because that means R2 and X2 is very small compared to the here. So this is very small, very less. Okay, and then we can simply eliminate the equivalent circuit into a new equivalent circuit, which is consists of, okay, still R1, okay, JX1, and then we have over here RC. So we have over here JXM, and then we have eliminate, or we have removed JX2, sorry, and R2, leaving only, okay, R2, okay, 1 minus S over S. Okay, so this is again nothing but resistance of friction and windage, F and W. Okay, so now we combine with F and W and also RC. Okay, and then we come up with this one here and here RC. Okay, the core resistance over here. So this we combine in parallel form. Okay, here, because this is nothing over here, this is nothing over here. This means F and W is parallel to RC and also JSM. So we parallel R and R. So to get a much simpler, let's see, I go over here, up here. So we have now RC R1. Okay. So we have JX1. Okay. Yes, we still have our JXM. Okay. JXM. But now we have a much simpler circuit R. This is actually RF. Okay, we have R C that parallel to R, F and W. Okay. F and W is all here. Okay, R21 minus S over S. Okay. So if we go like this, so you can see from your own slide, okay, before. So we combine RF and W and RC. Okay, so we have still our R1. So let me change the color. So we still have our R1 over here. Okay. So we still have our JX1 over here. Okay. And we just have JSM over here, and also the RF, NWN, F, and S core, which is much larger than XM. Okay. So what about the lock rotor test? So or the block rotor. So we have now the adjustable again voltage, adjustable frequency, phase 3-phase power. So we still have our ammeter over here to measure the current of each line or each phase. So we have the voltmeter to measure the line 1 between line 1 and line 2. So we have the power meter number 1. So we have the power meter number 2. So now we lock the rotor while it is running. To hold the rotor, so we know that Fr equal to Fe equal to F test. Okay, at this moment, so we know that Fr for the rotor frequency equal to the system frequency, electrical frequency equal to the test frequency. Okay. So what happened again at this condition, under this condition, so we have S equal to, remember, equal to 1. So rotor lock, so the rotor has been locked, no speed at all, so S equal to cos equal to S equal to 1. So what happened to IL? IL is approximately equal to IL rated. So we have IA plus IB plus IC over 3. So measure from this emitter, giving us the value of IA, IB, IC. So divide by 3 in order to get the IL rated. Okay. And then, okay, here, so AC voltage is supplied to the stator. So this is the step here. We start from here. So the AC voltage is supplied to the stator. So adjust current flow. So we need to adjust the current flow from the supply to full load value. And then at full load measure A, V, and also the power. Okay, this is the step on how to carry out the lock rotor test in order to get the value of ampere, volt, and also the watt. So this is again the equivalent circuit of the lock rotor test. So since Xm is much greater than R2 plus JX2 and RC much greater than R2 plus JX2, so we just neglect RC and Xm. Okay, because the value over here is too high. Okay, when the value is too high, let's say it is approaching affinity, let's say, so this means here is open circuit, is it? So open circuit means the value of R is, or JSM is affinity, is too high compared to R2 plus JX2. So we just neglect the RC and so XM. So the rest remain the same. So why R2 over S equal to R2? Because remember S equal to 1. So into here now R2 over S equal to R2. Okay, R2 over 1 or R2. So that's mean, so at the end of the day, so our equivalent circuit looks like a series connection. Okay, series connection consists of R1 element of JX1. So we have JX2 plus R2. So very simple equivalent circuit. So one problem with this test, during normal operating condition, S of the motor is only 2 to 4%, and resulting the F rotor, the rotor frequency is in the range of 1 to 2 Hz. Because why this happened? Because Fr equal to S Fe. Alright. So the problem is with this value of S. So the value of S is falling in between 0.02 up to 0.004 or 2% up to 4%. So just imagine we have Fe about 50 Hz, okay, or 60 Hz. So by multiplying 50 Hz with 0.02 or 0.04 or 60 Hz, for example, so you may get the value of frequency. The rotor frequency is about 1 to 2 Hz only, so very low. So this is the main problem. So the FE rated frequency 60-50 Hz does not represent the normal operating condition of the rotor. So this is again the problem. So So we have a typical compromise is to use a frequency F test 25% or less of FE rated, example 12.5 Hz and 15 Hz. So this is the minimum requirement in order to proceed with this particular test. We should have 25% of 50 Hz, okay, out of 50 Hz or out of 60 Hz. Okay, so this is where this figure is coming from. Okay, it's coming from 25% multiplied by 60 Hz, 50 Hz, or 25% multiplied by 60 Hz. Okay. So the input power to the motor, so you have P in equal to Vt to square root 3 Vt IL cos theta. So this is the equation, okay, the formula. So the magnitude of the total impedance in motor circuit, we have log rotor Z, the impedance, the magnitude. So we have this over I1, so we have Vt over square root 3 IL. So V log rotor equal to R log rotor plus Jx prime log rotor. So the magnitude of ZLR cos theta plus JZLR, again the magnitude sin theta. Okay, and then thus we are able to get the value of RLR. So the load rotor resistance, which is consists of R1 plus R2, and also the X prime LR, X1 plus X2 prime. Okay. So the total equivalent reactance of at normal operating frequency, so we have XLR. So the reactance, log rotor reactance, so we have F rated over F test multiplied by or times X prime LR equal to S1 plus X2. Okay, so this is when you, okay, this is for the data connection. Okay, here, so this is essentially for data connection. Sorry, I forgot to mention about that. So this is this analysis or this test will be much more interesting when you come or you further your study in master level, I believe. Okay, so some of the analysis will be further shown or will be further discussed at master or postgraduate study. All right. So now the last but not least, the rating of the induction motor. This is example of the nameplate, the birth certificate available on the body of the motor. So what it shows, so it indicates the output power of the machine, so the voltage, the current, all right, so the power, output power, it may be in horsepower, for example. Okay, so the I, all right, so the cos theta or the power factor, and then the speed, okay, and then the nominal efficiency. So this is to show you how efficient the motor is. We have 90%, 90%, for example. So the nominal efficiency means it represent the mean efficiency of a large number of sample motors. So it come up with a sampling of the motor, and then the guaranteed minimum efficiency that represent the lowest permissible efficiency for any given motor. Okay, for example, the nominal frequency efficiency of the motor is around 95%. All right. So and then out of the same thing of the same class of the motor, so it shows that the guarantee minimum efficiency of the motor is 94.1%. So this is what have been gone through experimentally, for example. All right. And then this is what I have mentioned earlier, NEMA, so National Ethical Manufacturing Association. So design class, it has it fall between this range, class A, B, C, and D, and also the starting letter, code letter F I mentioned earlier, in order to calculate the inrush or the starting current. Okay, that's all for now. Thank you very much for watching. So see you in chapter 4. Have a nice day.